Welcome back to Statistics. I'm Dr. Jeff Groh. Today we're going to talk about estimating a mean. In particular, confidence intervals for the mean. As you know, the sample mean is an estimate for the population mean, but it is a point estimate. It'd be better to have some kind of confidence interval so we can tell how good that estimate is. The method that we are going to derive here implies that either the population is normal or the sample size is large. And when we say large, what we really mean is bigger than 30. 30 is being the cutoff for using the normal distribution for the sample means. For small sample sizes, or when the population standard deviation is unknown, we use the T statistic. The T statistic is just like the Z statistic. Z was what? X minus mu divided by sigma. For the T statistic, it's going to be X minus mu divided by S over the square root of the sample size. This statistic is sometimes referred to as students T. Back in 1909, a man published a paper under a pseudonym named Student. And so this has come to be known as students T statistic. And we have, just like we had a distribution of z-scores, there will be a distribution of t-scores as well, the students T distribution. There are two things we have to add about this. First of all, that there's something called degrees of freedom. What you need to know about that right now is it's denoted by df, and it will be the sample size minus 1 when we're dealing with confidence intervals for the mean. Also, because there is a student's T distribution that looks similar to the normal distribution, there are going to be critical t-scores. As well. How does the confidence interval work? Fortunately, this works just like other confidence intervals you've already learned. You'll take this sample mean minus a margin of error and the sample mean plus a margin of error, giving you the endpoints of the confidence interval. How is the margin of error calculated? Instead of using a critical z-score, you'll use a critical t-score times the sample standard deviation divided by the square root of the sample size. I have to say, there is a t-inverse that you can use for finding the critical t-scores. There's also the t-interval feature in your calculator that you can use for just calculating the confidence intervals. For example, the blood pressures 25 elderly women have mean systolic measurements of 140 millimeters of mercury. If this data is considered to have been taken from a normal population that means a population of systolic blood pressure measurements having a normal distribution, with a standard deviation of 10 millimeters of mercury, find a 95% confidence interval for the mean. We'll do this a couple different ways. Notice that 1 minus alpha, the confidence level, is 0.95, 95%, which means alpha is 5%, and alpha over 2 is then 0.025%. Again, if you have 2%, 2.5% over here, then you must have 97.5% over here, or an area of 0.975. The T inverse function only gives you areas from here all the way to negative infinity. So I'm going to go to second distribution. It's inverse T this time. The area is, of course, 0.975. The degrees of freedom. The sample size was small, only 25. So the degrees of freedom will be 25 minus 1, or 24. And so that gives us the critical T of 2.064. We're given the mean in the problem and a standard deviation of 10. So the left-hand endpoint will be 140 minus our 2.064 times 10 divided by the square root of 25 to 140 plus the same thing. Crunching this on the calculator, 140 minus 2.064 times 10 divided by 5. So the lower bound is 135.9. And on the upper bound, 140 plus 2.064 times 10 divided by 5. 144.1. And so there's your confidence interval. We can also use this by pressing the Stat button and going over to Tests. And we can go down to, so the Stat button, go over to Tests, and select T interval. So in this case, you can either input some data that you have. Well, we don't have a list of data. All we have are the statistics. So we're going to use stats, not data. I'm not going to select that option. The mean that we're given is 140. And it gives you an SX, that's the standard deviation for the data. In this case, that's 10. N in this case is 25. And the confidence level is 0.95. What does it output? 135.9 to 144.1. Exactly as before when we calculated this using this formula. Here's another example. 64 randomly selected students took a placement exam. The average time to complete the exam was 28.5 minutes, and the sample standard deviation was 3.050. Find a 95% confidence interval for the mean test completion time. In this case, the sample's big, but we only know the sample standard deviation, so we will use a t-statistic for calculating the confidence interval. The sample size was 64. The mean was 28.5 minutes, and the standard deviation was 3.050 minutes. We're looking for a, I'm going to change this to a 99% confidence interval. Going to Stat, Tests, T-interval, we'll use stats again. The mean was 28.5, standard deviation 3.050, N is 64, and the confidence level is 0.99. So how big is the interval? 27.49 minutes to 29.51 minutes. This gives us a 99% confidence interval. Whatever the mean is, mean completion time, it will lie somewhere within this interval with 99% confidence. Now, we could have done this with critical t's. Alpha would be 1%. So we'll have to take 0.5% as the area that we use, half of 1%. We'll use the t inverse, or the inverse t, That's second distribution, just above the vars button on the calculator. The area is 0.995. The degrees of freedom will be 63. Yielding a critical T of 2.656. So we can use the mean, 28.5 minus 2.656 times the standard deviation, 3.050, divided by the square root of the sample size to get the lower limit, and the upper limit only differs by turning the minus into a plus. And you can check that you get exactly the same values as before. What are the properties of students' T distribution? First, you get a different shaped curve, slightly different shaped curve for different sample sizes. They're tweaked ever a little so differently, but that will have a significant impact on the confidence intervals that we produce. They are symmetric and bell-shaped. They have slightly larger standard deviations than the normal curve. The mean is 0 for these always. The standard deviation is bigger than 1, and it depends upon sample sizes. And finally, the curve, the t-curve, tends to the normal curve as n goes to infinity. So the larger the sample size, the closer the student's t distribution is to the standard normal curve. In 16 one-hour test runs of an engine, they averaged 16.4 gallons of fuel with a sample standard deviation of 2.1 gallons. Find a 90% confidence interval for mean fuel consumed in 1 hour. So in this case, the sample size is small, so no matter what, you're going to be using the student's t distribution. But in addition, you only have the sample standard deviation, so you would have used student's t anyway. In calculating the confidence interval, we can simply use stat tests t interval. So it's t interval again. Stats is the option that we choose. The mean is 16.4. Standard deviation is 2.1. N is 16. The confidence level is 0.90, since we want a 90% confidence interval. And we get 15.48 to 17.32. And these are gallons on the 1-hour test run. We could have done this with an inverse t. Going over to second distribution, t inverse. The area is 0.95. Since we have a 90% confidence interval, that leaves 5% in the right tail, 95% to the left of that right tail. The degrees of freedom will be 15. We get 1.753 for the critical t. Let's just check one of these. We'll check the right-hand endpoint, 16.4 plus 1.753 times the standard deviation 2.1 divided by the square root of 16. I'll type that in, 16.4 plus 1.753 times 2.1 divided by the square root of 16. I am getting 17.32, just as before with the t interval command on the calculator. I'd like now to discuss estimating sample size. And we'll use margin of error for this. But we can't use critical t-scores here because in order to get a critical t-score, you already need to know the size of the sample. The best you can do is critical z-scores. We'll solve for n, whittling away at the things surrounding n, starting with the things furthest away by the order of operations agreement. And we use opposite operations, so since the critical z is multiplied here, we'll divide it to the other side. We'll have to invert both sides to get the n into the numerator. Multiply both sides by the standard deviation, and then square both sides to yield the final formula. N is your critical z times your standard deviation divided by the margin of error squared. Let's do a quick example. Let's suppose that we want a 95% confidence level. A standard deviation of 3.5 and a margin of error of 0.9. Find the sample size. First, we need to find the critical z. Notice that the confidence level is 0.95, which means alpha is 0.05. Alpha over 2 is 0.025, 2.5%. And so the area that we'll use in our inverse normal will be 0.975. We go to second distribution, inverse normal, area is 0.975, mean and standard deviation are 0 and 1. We use the left tail, and we'll get the critical z of 1.960, rounded appropriately. That's our critical z. The sample size will be our critical z, 1.960, times the standard deviation, 3.5, divided by the margin of error, 0.9, and then squared. So I'm getting 1.960 times 3.5 divided by 0.9 and then squared. This gives me 58.098 yada yada yada. Remember, you never round these down. We will choose 59. No matter how close that is to 58, we'll always bump it up